So we're going to wrap up our study of logic and our class by talking a little bit about predicate logic. So just so that you remember, we've been talking so far about propositional logic, and hopefully you remember that a proposition is just a statement that's either true or false. So it could be Kermit the Frog is green, or 2 + 2 = 4, or the number 8 is prime, right? And we often abbreviate these and turn them into woofs. Like we could say let A equal Kermit the Frog is green, and let B equal 2 + 2 = 4, and let C equal 8 is prime. And so we could come up with A and B and not C. And it's an interesting statement, okay, or a not so interesting statement, but it's something that we could do if we want to. Now, we have been talking about, like I said, propositions, right? Which is just a true or false statement, like Kermit the Frog is green. Predicates are more like functions or methods. It is a function, I'm going to call it for lack of a better name, that takes a parameter, right? And it returns true or false depending on what the function is about, what the predicate is, and what the parameter it gets is. So for example, we could say, let's let g of x mean x is green. By itself, a predicate doesn't actually have a truth value, right? A truth value, it's not true or false. If I just say g of x means x is green, that's not true or false. It only becomes true, we can make it, or false, we can make a proposition out of it, out of a predicate, if we use some sort of a constant as the argument or parameter for the function, right? So if I let k equal Kermit the Frog, then g of k means Kermit the Frog is green, and that can be either true or false. And in fact, I could also say A, right? This A up here equals G of K, right? So A is the statement Kermit the Frog is green, and here I have G of, with the argument K. All right, so just a couple more examples. Remember that a predicate is, kind of a function or a method that returns true or false, right? So we could say, let g of x mean x is green, and let f of xy mean x + y = 4, and let p of x mean x is prime, and let b of x mean that x has a banner ID. And we could set some constants, like let's let I equals 3, and let's let j equal 6, and let's let k equal Kermit the Frog, right? And then we could say g of k, in other words, Kermit is green, and it's not the case that Kermit has a banner ID, and the number 3 is prime, and the number 6 is not prime, and 3 + 6 does not add up to 4. Okay, so just to review, we have talked about 3 different things so far, and I want to make sure you have them down and know which is which, right? We started with a predicate, which, because we're computer scientists, I'm just saying is a function or a method that returns a Boolean, right? It returns true or false, right? Given a parameter. We also have a variable, and a variable is what we refer to as the arguments of, or the parameters of the predicate that could take on lots of values. So the x in here in g of x is a parameter, right? We could turn that into k for Kermit the Frog, right? And x and y here are parameters or arguments. We're going to call them variables in this predicate, right? And then finally, we have some things that are constants, and they can be specified with a single letter, or also they can be used to, we can write them out as sentences, right? Kermit the Frog, the number 42, my pink baseball, right? And we could put a constant in substitute a constant in for this variable, and then we could say things like g of the number 42, which would be a statement that says the number 42 is green, and then we decide whether that's true or false. Now, honestly, that doesn't really seem much different from the propositional logic that we've been doing. But let's talk about what happens when we get into larger collections of items. And to do that, we need to start talking about a domain, right? And not domain as in domain and range, but domain as in what is our universe that we've used. Maybe we've used the term universe in when we were talking about sets, right? So, for example, if I set my domain to be Rowan students, right, and leave B of X as has a banner ID, I could make a statement that says every single X in our domain has a banner ID, right? For all X in our domain, B of X, all Rowan students have a banner ID because I limited my domain to banner students, so everything in my domain has a banner ID. Now, of course, if I change my domain and say, oh, now my domain is American citizens, right? But I leave my predicate alone, B of X means that X has a banner ID. Well, now I could make a statement that says something like, it's not the case that for all X in our domain, B of X, right? Because not all American citizens have a banner ID. If I leave my domain as American citizens, I could make more statements using this predicate B. For example, I could say, you know what, there's at least one X in our domain such that B of X. So there is at least one American citizen who has a banner ID, right? So even though all of the X's, all the elements of our domain, B of X is not true, there's at least one of them for which B of X is indeed true. So you can see we've got sort of more complex concepts that we're doing with predicate logic than we had with propositional logic. So let's go back to our old domain of Rowan students, and we'll still have that predicate B. We could also say there exists at least one X in our domain such that B of X, right? There's at least one Rowan student who has a banner ID. And that's true. Of course, you and I happen to know that all Rowan students have banner IDs, and so that first example that we used was perfectly valid, but so is this, right? It is definitely the case that there's at least one Rowan student who has a banner ID. There's a lot of Rowan students who have banner IDs. So as with much of this course, we end up taking shortcuts in terms of our notation. And we're going to use this funky upside down A, which, you know, if you go to a party and you want to talk about it, you could talk about the universal quantifier. But in fact, most people just translate it as for all. So if you see an upside down A, you have to think for all, right? So if we go back to that example where we were talking about our domain was Rowan students and B of X meant X has a banner ID, if we write this statement right here, for all X B of X, that says all Rowan students have banner IDs, right? Similarly, if we do a different example, let me cross out this example, and we say, oh, you know what, our domain is actually American citizens, we could say this statement, right? And look at my parentheses here. Let me see if I can make this a little bit bigger. Okay, so what have I got here? I have got a not outside of this statement. So this statement is saying for all X in my domain, right, it is the case that X has a banner ID, except outside I've got my not, so that means that, that means that our statement is it's not the case that all American citizens have banner IDs, right? It is not the case that for all X, B of X in our domain. And I don't suppose you'll be terribly surprised to find out that there's not one but two of these nice shortcut symbols. This kind of upside down backwards E, mirror image E maybe, is called, the fancy name is the existential quantifier. But again, it's just a fancy label for a lazy shortcut. We're going to use that backwards E to represent the phrase there exists. So if we look at this first example, where my domain is Rowan students, this backwards E of X, B of X means there is some value X in my domain for which X has a banner ID, right? So specifically, there is some X in my domain, where my domain is row and student, so there exists a row and student that has a banner ID, right? And this there exists means at least one, right? There could be 10,000 of them, or there could be one. But if you have the backwards E, that means there exists, the existential quantifier. And again, if we look at this other example here, and my domain is now American citizens, I can actually make the same statement, right? There is at least one element of my domain of American citizens for which that element, that person, in fact, has a banner ID. So let's talk about how to translate some English sentences into predicate logic. Okay, so let's suppose that my domain is all people. Right? So here's my domain, all people, and let H be the is human predicate. And I want to say everyone in my domain is human. Right? Well, how do I say that? I say all things in my domain are human, right? It's a nice big way to write it in English. Using predicate logic, we just write for all x, h of x. Everything is human. Okay, here's another example. Same domain, we still have the domain of people. We're going to have B this time represent the predicate has brown hair. So I want to say there exists at least one person with brown hair. Well, I said there exists, didn't I? At least one person has brown hair. There exists some X. You know, I don't have to use X. I could say exists a Z. Let's be exciting. Okay? There exists a Z such that B of Z. Right? This Z here, this X here, we'll talk more about this later, but it's like a local variable in a method, right? It whatever we use here and here, as long as they're the same, they're kind of coupled. So let's let B be the has brown hair predicate. And now I want to say there's more than one person has brown hair. And this gets a little bit trickier. In fact, I sort of need to give you another predicate for this. Let's say let's make a new predicate called N, which is the not the same predicate, which will take two parameters. So if I want to say more than one person has brown hair, what I have to say is there's two people. There's at least two people with brown hair, right? So I have to say something like there exists an X and there exists a Y, right? So there's an X and a Y such that X has brown hair and Y has brown hair. And furthermore, I didn't give myself enough room. So X has brown hair, Y has brown hair, and furthermore, X and Y are not the same person, right? And this is a little bit more complicated, right? Because now I'm using two of these for there exists, right? Which is a little bit different. But you can see, by the way, I parenthesize these, right? There's parentheses, the biggest parentheses in here is around these guys, that all of these predicates are inside of the parentheses, and they're kind of governed by this. So there exists both an X and a Y such that X has brown hair and Y has brown hair, and this is very important, X is not the same as Y, they don't equal. Okay, here's another example. We're going to let G be the has green hair predicate, very exciting, in our domain of people, and we're going to say no one has green hair. So how do we say that? No one has green hair means there's not even one of them, right? And in fact, we could write this two ways. The first way we could write it is we could write kind of the opposite of there exists one, right? So there does not, it is not the case that there exists, maybe we'll go for Y, exists a Y such that G of Y, right? So that's one way to write it, is there does not exist anybody in our domain which has green hair. Another way we could write this, which is putting across the same idea, it's the same exact concept, but said a little bit different, is we could say everybody doesn't have green hair, right? So we could say something, I'll do this in red instead. For all x, it is the case that not g of x, right? So no matter what x you take in my domain, all of them do not have green hair. And when I look at these two equivalent statements, they sort of remind me of De Morgan's. It's not exactly the same here. But to me, if I have a there does not outside of this exist, that's actually the same as for all there isn't pushed in. Okay, so we're still dealing with the people domain, but now we have a predicate with two, I'm going to call them parameters. And if I want to say everybody has a parent, right? What do I have to say? Everybody has a parent. And these translations get hard, and the first time you see them, they're particularly challenging, but as you kind of see me do some and you read the book and look at some examples, I think this will get easier. But so everybody has a parent. Well, we've got to talk about two people here, right? We're talking about everyone, right? So we know we have something about for all x, right? So all people, well, everybody has, and it doesn't say has one or more parents, but I guess we're going to say everybody has a parent. So we won't go for the exactly one right now. Everybody has a parent. So for all x, there is somebody, right? So for all people, there exists a person such that, let's see, we want x is the parent of y. So I guess parent, I did this the wrong way around, but that's okay. All right. So this says every person in the world, there exists somebody where that somebody is that person's parent. Now, it's possible, it's not really true, but it's possible to say that everyone has exactly one parent. We could also say everyone has exactly two parents, but that gets a little bit tricky. If we could say everyone has exactly one parent, what do we have to say? We have to kind of say this piece that we already have, right? Everybody has a parent. And then we want to say there's only one. So, one way we could do this is we could say, all right, for all x, there exists a y such that y is x's parent. And it's also the case, and I'm going to wrap around here, that for all x, if y is x's parent and z is x's parent, then they better be the same person, right? Let me shrink this a little bit more so I can fit it. Why is this not shrinking? So let's see what we've got here. We've got everybody has a parent, right? Everybody has at least one parent. And everybody, if y is their parent and z is their parent, well, I want to say that means that y is the same as z, right? So let's see. So that implies that, and I guess we could have a, let's add another predicate. Let's have EQ of x and y mean that x equals y, right? So if there's two people, y and z, who are both the parents of x, that implies that actually there's not two people, that y and z are equal. And now let's just make sure we've got our parentheses right. Let me make a little bit more room here. There we go. So let's see, we've got this piece here. For all x there's some y such that y is x's parent. And for all x, if y is x's parent and z is x's parent, that implies that y and z are equal. Okay, let's try this one. This one is not everyone is a parent, right? So what we have to say is either there is somebody who's not a parent, right? Or it's not the case that everyone is a parent, right? So what we have to do is we have to say, let's try it's not the case that everyone is a parent. So it is not the case that for all, maybe I'll start with z because I haven't used z much. It's not the case that everybody has somebody who they're a parent of. So it's not the case that everybody, for all z, there is somebody, there exists, I don't know. Why don't we make it make it an x. So it's not the case that all people have somebody, and now I just have to say who they're the parent of. So where z is the parent of x, right? So what did I say here? I said it's not the case that all people z have somebody x who they're parents of, who they are a parent of, right? That means that z is not a parent, right? Or I could say there are some people who are not parents of anybody, right? So I could also say there exists somebody, and maybe, oh, what the heck, I'm going to use really weird letters here just to make a point. There is somebody called A, such that for all other people B, A is not B's parent. So let's put a not there. It's not the case that A is the parent of B. All right. So that's another way to do this. And you can see, I hope, that these are two ways of saying the very same thing. Okay, here's a statement that says some people are parents, right? Let's take this a little bit. Let's take the definition of some as what do you want to do? We could do some as there's at least one person, or we could do some as there are multiple people. I think some tends to make me think multiple people. So why don't we add an equal of x and y predicate, which means x is the same as y, right? So some people are parents. That means there exists at least two people who have somebody, each of whom have somebody who's their child, right? So there exists an x and there exists a y such that x is the parent of somebody and y is the parent of somebody. So I guess we need the child of x and the child of y. Maybe we'll call them q, all right? Such that parent of, let's see, so x is the parent of c and y is the parent of q, and x and y are not the same. So it's not the case that x equals y. So again, if we look at this, there are 4 people here, right? Possibly in this group. And I've said x is the parent of c, y is the parent of q, and the only, this is anywhere between 2 and 4 people, right? Because the only thing I've told you is for sure x doesn't equal y, right? I told you that down here. So this statement says there's somebody x who's the parent of c, there's somebody y who's the parent of q, and I guarantee you x and y are not equal. It may be that x is the same as q, or y is the same as c, or x and c and q are all the same people. That's possible, but I told you for sure x and y are not equal. Okay, here's another one. let P of xy be x is the parent of y, predicate again. No one is their own parent, right? So there is nobody who is their own parent. This is actually an easy one, right? There does not exist an x such that x is their own parent. That was a nice, easy one. And of course, we can flip that into a for all as well if we want, right? It is the case that for all x, it is not, x is not x's parent, right? So no matter what x you pick in my domain, it's not the case that x is x's parent. So again, these two are actually equivalent statements. They mean the same thing in English, even though they look a little bit different. Okay? There is no one person who is everybody's parent, right? So what am I trying to say here? Let's see. There does not exist a person y so that for all people x, y is x's parent, right? There's no one person who is the parent to everybody else. Now, sometimes we don't want to really specify the domain, and so we can just sort of specify the domain by the predicates that we use. So for example, if we want to say not all birds can fly, we could say that there is at least one thing that is a bird that cannot fly. So we could say there exists an x such that x is a bird and x cannot fly. Now you can think of this as in two ways. You can say, oh, I have no specified domain, or you can say my domain is everything in the entire universe, and this still works. Now in colloquial English, this is a little bit ambiguous. Some birds can't fly. If we think that that just means a single bird, you know, there exists a bird that can't fly, we've got much the same statement, much the same predicate, wolf, I suppose, as we had before, right? There exists an x such that x is a bird and x can't fly. Now, it's possible that we wanted to talk about multiple birds that can't fly, and so we could talk about how there's at least two of them that can't fly, right? And we'll use that not equals trick again. So we could say, for example, there's two things. There exists at least one x and one y, such that x is a bird and y is a bird, and I'm going to start using a shortcut here. I'm going to say x does not equal y instead of using a straightforward predicate. I'll just use this inline equals, just like we do for when we're programming. We use equals inline, or we use equals equals, right, or does not equals inline, instead of using a method. So what have we got here? We have, there's an x and a y such that x is a bird, y is a bird, x doesn't equal y. All right, and we need to keep going. And x can't fly, and also y can't fly. Okay, here's another example. All days are sunny. So it's the case that for everything in our world, if it's a day, it's sunny, right? So for all x, if x is a day, then x is sunny. Some days are not rainy. Let's take this colloquially to mean there's at least one day that is not rainy. So we want to say there exists an x such that x is a day and it's not rainy on x. Here's a little bit of a weird one. Every day that is not sunny is also not rainy. So this is talking about everything, right? For everything in our world, if it's a day and it's not sunny, then it is also not rainy, right? So for all x, if x is a day and, let's see, not sunny, then X is not rainy either. Let's shrink this a little so you can see all the parentheses. So I think we've got them right now. Let's see. So this thing, if this whole thing is true, that implies this little piece. And there's the outer ones. And so this X is covering all of that. Some days are sunny and rainy. So again, let's just use the colloquial some to mean there's at least one, right? So there is a day which is both sunny and rainy. There exists, why don't we do Q just for a change? There exists a Q such that Q is a day, and Q is sunny, and Q is rainy. No days are sunny and rainy. Now we've got there are no days, so there does not exist any, or for any day you pick, all the days are not sunny and rainy. So let's say there's no day, there does not exist a day. So it's not the case that there exists an X where X is a day and X is sunny and X is rainy. Now, so far I haven't actually talked about these constants over here. We can talk about constants just like we do in programming, and we can say things like, suppose M represents Monday and T represents Tuesday. If we want to say it rained both Monday and Tuesday, we're talking about two specific constant days now. We could say something like Monday was rainy and Tuesday was rainy. Or we could say something like Monday was sunny, so it was sunny on Monday. Therefore, every day will be sunny. So if it was sunny on Monday, that implies that for all X, sunny of X. Now notice that this is kind of interesting because we sort of have some variables that are what we're going to call bound, right? This X here is referring to just kind of a variable X, right? Where we said that's true for all X's. Whereas right here we have this constant Monday, so we're saying because it was sunny on Monday and there's no existential quantifiers, no universal quantifiers, right? No for alls, no there exists. That implies that for all X, it will be sunny. And we'll talk more about this in a little bit. Now, the truth is we don't actually need to know the meaning to work with predicates. So your book says that for the most part they're going to use X, Y, and Z as variables. They're going to use A, B, and C as constants, and P, Q, and R are going to be the letters representing predicates. So suppose I tell you here's a fact, all right, that P, which is some predicate of A, and P of B and P of C, that these guys, that this wolf is a tautology, right? This is true. What can you conclude? This is kind of a weird question, but you'll see in a minute. What can you conclude if I tell you that my variables are going to be in the domain, which is the set containing A, B, and C, these three constants? And let me show you where I'm going here, and after this I think you'll get it. If you know that the predicate is true of A and of B and of C, and that my domain just involves A, B, and C, well, then I could say for all X, P of X, right? So everything in my domain, P of X is true because my domain is pretty small. I can also say there exists something in my domain for which P of X, because it's true for all of them, there's got to be true for at least one of them. So suppose I make the same statement that this predicate is true for A and B and C, but I change my domain. Now my domain is the letters A through F. What can I conclude now? I can't say it's true for all X anymore, right? Well, in fact, I can say there's at least one of them, right? And I can say it's not true for all of them. So here's another woof that I want you to look at with some predicates and try and figure out what can we conclude. Now notice that I have changed it from and to or, so I know P of A or P of B or P of C, and I'm back to my original domain here. What can you conclude? Pause for a second and think. Well, since this is an or, we can conclude that one or more of these is true. So that's there exists an x, P of x. I don't know which one. It may be all three. It may just be one. Now, if you look at this one, I've really messed with it. I have P of A or, and then these two are ANDed together, P of B and P of C. So what can you conclude if I tell you x is in A, B, and C? Well, again, I'm kind of saying you can conclude that there's at least one, right? Because we know that either it's P of A or P of B and P of C. And there's probably more than just this you could conclude, but you can certainly conclude that there's at least one, right? I mean, we could go further and we could say, well, if P of B is true, then P of C is also true, or something like that. But just at its simplest level, that's what we can conclude. Okay, I seem to have changed my predicate now. The meaning of the predicate is something different because it now takes two parameters, right? Let's see, what do we got here? We know that P of A comma B and P of B comma B and P of C comma B. And if I tell you my alphabet is A, B, and C, can you think of anything that we could use the for all or there exists with respect to this P, this predicate? Well, how about this one? No matter what x you choose in the whole universe, right, which isn't very big, in my whole domain, this predicate is true for x and b, right, because it's true for A and B, it's true for B and B, and it's true for C and B, right? So it's true for all of those things, anything in my domain. And of course, since it's true for anything in my domain, it's also true for at least one thing in my domain. So far in this lecture, we've been using any old letter to represent whatever we want, right? So, for example, we've used B for a bunch of things. Like we've said that let B be a constant, right, in one place. We said let B equal 2 plus 2 equals 4, right? It was a proposition. And then we also had B be a predicate. B of x meant x had a banner ID, right? And I just want to let you know when you're reading your textbook, the textbook likes to save space. We know that. And in this case, it's going to save space by saying things like, whenever you see an A or a B or a C, you can assume that it's a constant, right? So here's sort of the full list of the things that are important when you're reading the book. It's not something I'm necessarily going to do in this lecture, but just to sort of point out that the book is going to talk about variables. When the book uses a variable, it will always be X, Y, or Z, right? When the book uses a constant, it will always be A, B, or C. When the book uses a predicate, it will always be called P, Q, or R, right? Unless they state otherwise, but I'm not even sure they ever do anything different, right? They always use X, Y, and Z if they want a variable. They always use A, B, and C if they want a constant, and they always use P, Q, and R if they want a predicate. But don't hold me to this. I may not do that. Okay, so now that you have a feel for how these predicate logic woofs work, let's just look at the rules of precedence for a minute. Effectively, it's exactly the same as we use for propositional logic, except we add on the rule that if you have any quantifier or the negation symbol appearing next to each other, then, and what we say here is, and this is actually a quote from the book, the rightmost symbol is grouped with the smallest woof to its right. So in practice, what does that mean? Well, if you look at this first one, actually let me move the rule down a bit so you can see it. So the rightmost symbol is grouped with the smallest woof to its right, right? So here's the rightmost symbol in this first one. It's grouped with these guys, right? And then, so here we go. So this right one, this is with the parentheses, right, is grouped with that. and then we take the next one and group it with the stuff to its right. So this exists to y has the parentheses around that, the not connects to everything else, and the for all x connects to everything else. And I've made such a mess of that now that you can't really see it. So let's see if I can get rid of all those little red lines. There you go. Okay. Let's keep going and let's look at the second one here. So the second one is interesting because we have this exist x, right? It's going to go with the smallest woof that it can to its right, which in this case is just this p of x, right? So if you look over here, these guys got grouped together. So it says there exists an x p of x or q of x. That's all one thing, or q of x. So notice that this x here isn't actually a part of this exists in x. We'll talk about more about that in a little bit. Let's look at this third one here. For all x, p of x implies q of x. Again, this for all is going to get the smallest thing it can next to it, which is just this p of x. So it looks a little bit weird when you parenthesize it, but that's what the rule says to do. If we look at this one, right, there's this exist in x, but this not is to the right of it. So this not is grouped with this predicate, and then the exist in x is with this big predicate, so we end up with the not with that first one, the exist with this whole thing, and then the implies is to something else entirely, right? And finally on this one, this exists wraps with the closest thing on the right, the for all wraps with the closest thing on the right, and you can see that happening over here. Hopefully most of the time you will just parenthesize stuff because it's such a pain when it's not put in parentheses. It's too easy to make a mistake. But this is a rule that's pretty straightforward. Okay, so you guys know about scope in terms of programming, and I've kind of referred to this in the lecture already without really being very, very specific about it. So now we'll talk about it carefully. So if you have an existential quantifier like there exists an x w, the scope of the existent x is w, right? So this x is kind of in scope in w, right? Scope of for all x in this is w, and so and so. In the absence of parentheses, the scope of a quantifier is the smallest wolf immediately to its right. Yeah, boring. Let's just keep going and look at this. It's often so much easier when you look at an example, right? So if we look at this first wolf here, I'll make it bigger, but not so big you can't see anything. This first wolf, we have this for all x, p of xy implies q of xy, and you know from the parenthesizing we did before that the for all x actually just goes with that piece, right? And so what's the scope of for all x? It's just that piece. On the other hand here, you can see I kind of parenthesized that whole thing, right? So what is the scope of the for all x here? It's that whole thing, and that's what the table says. The scope of the for all x is that whole thing. Getting a little bit nastier here, but let's take a look. Here's this for all x, and what's the scope of this for all x? Well, let's see. That parenthesis goes all the way to there. So the scope of the for all x is all the stuff inside. If we look at that same equation, but say what's the scope of the existential quantifier on y, the exists of y, right? We got to look and get our parentheses right here, but let's see. I think that one matches with that, and the exists of y goes around all that. So what's the scope of the exists of y? Well, the scope of the exists of y is this whole piece here, right? And I hope this is making sense. What's the scope of the for all z? Well, the for all z is just over that stuff, so same thing there. And that's it for this slide set, and in fact, that's it for the class. So thanks for coming along with me for the ride. It's been a lot of fun.